What is up? Welcome back to 3.5 this time. Is the chain rule. So we've kind of already touched on the chain rule last time with the differentials, with the total differentials. These are called total differentials. I don't know if I actually covered them or not because it's been 2 weeks since I've actually recorded the last video. I'm behind, I'm sorry. But these are called the total differentials for the function, and they can be written like this, as in df is equal to partial f partial x, right, f sub x dx plus f sub y dy, and it would make sense because of the tangent plane approximations that we had last week. Now, it's the same thing for x, y, and z, right? If you had a tangent hyperplane, if you had a linear approximation for maybe the temperature at a point, and you want to see how much that temperature changes in regards to x, y, and z coordinates, you can linearize your you can linearize your surface. You can linearize your, I guess you could say, equation near that point, so that you will get a better, more accurate estimation for that point, instead of just using a point that's right. So we have something that is close to that, like this right here. Find the total differential for f of x, y, z is this, then approximate the function at this. So we kind of already did it last time, but let's do it one more time to see if we can find a better way, find like an insight. We probably won't. But anyways, find total differential for this, and then approximate the function at this. So we can go through the steps again. First, we want to find a point that is a little bit easier to not differentiate, a little bit easier to wrap your head around than 0.1, 0.91. Okay. The thing about finding a point with this function is that you don't really get very nice points for this function, and the reason is, or you don't really get like a good estimate, because sine only works well for pi numbers, and e works well for non-pi numbers. It doesn't work well for pi numbers. So the point that I'm actually going to pick is 0, 0, and 1. Now, do you have to worry about this on the test? Probably not. But I'm going to pick 0, 0, and 1 because the point of getting an approximation is to get nice numbers. And if we don't get nice numbers from approximation, why care about the approximation? I think I also had a trouble like this last time. So I could pick 0, 1, and 1. That would be closer, but I pick 0, 0, and 1 because I think that is better. And it's better for the approximation. So 2, I'm going to evaluate f of 0, 0, 1. I might be doing the steps out of order a little bit, but f of 0, 0, 1 is sine of 0 is 0, so it's 0. Right? Number 3, let's find f sub x, f sub y, and f sub z. So what's f sub x? F sub x is sine y is a constant, so sine y, and then e of x plus y minus z. Because e copies itself, y and z are constants, so e just copies itself, and we multiply by the derivative of the inside, but y and z are constants, so they reduce to 0, and x just, I guess you could say times 1 for good measure, but there is no point. So y is a little bit more complicated. I'll tell you that if you do z by yourself, you should do z by yourself right now. 3, 2, 1. Okay, if you do z by yourself, you will have a negative in front like that, and then you will get this. You'll get a negative in front. Y is a little bit more complicated because both functions that we have include y. So what we're going to do is we're going to take the derivative of we're going to keep the first derivative of the second, which is just the same thing again, and then plus the second, or the derivative of the first, times the second. Okay, those are your functions. They are really nasty. Really, really nasty. They're not nice at all. right? So now what we're going to do, now we're going to find f prime, or no, not f prime, we're going to find f sub x, f sub y, and f sub z at 0, 0, 1. So I'm going to kind of squish this. Oh gosh, no, don't squish this. So at 0, 0, 1, we'll have f sub x is equal to f sub y. Notice that this is not a tangent plane. It's more like a tangent hyperplane, but it's just a linearization. It's just making the function like a linear function so that we can solve it easier and without much hassle. So at 0, 0, 1, sine y e x, that's the exact same thing, so it's 0, right? At 0, at whatever this is, sine y e x plus y minus z plus cosine y, right? This is approximating the function. I'm not actually writing the differential yet. So at 0, 0, 1, this is 0. At 0, 0, 1, that's 1. And then we have 0 plus 0 minus 1. So 0 plus 0 minus 1 is 1 over e, right? Which is not a very nice number. I mean, it's kind of just tough. Not a very nice number. And f sub z, sine y is 0, so it's 0. Right, so the approximation that you actually end up getting is, well, first of all, let's write the total differential. So step 5. That's step 4. df is equal to f sub x dx, right? I don't... Let's see if this works. F sub x dx. There you go. F sub x dx plus f sub... Oh gosh, this is going to be even squished even further. F sub y dy plus f sub z dz. There you go. Now, we know that our f sub x is 0 at that point, so well, we can change this. First we can change df, dx, dy, and dz into delta f, delta x, delta y, and delta z. But like it's like f minus f0 basically. So f minus f0 equal x minus, or equals 0 times x minus x0 plus 1 over e times y minus y0 plus 0 times z minus z0. Right, this is not going to get us a very good approximation, as I've said before. Right, let's make this smaller. And then our f0 is 0, right? F of 0, 0, 1, that's 0. So our f at the original point that we don't really care about is 0. So f is equal to, that crosses out, 1 over e times y minus 0, because f at our original point is 0. So our y is 0.9. So f is simply, or f is or I'm not going to say equal. Right, this is approximately. So f is approximately 0.9 over e. F at 0.1, 0.9, 1.1, 0.1, 0.9, 1.1 is approximately e. 0.9 over e, I'm sorry. 0.9 over e. Okay, next slide. Find the derivative dy dx. Okay, we're going to go back to implicit differentiation. We're going to do this two ways. We're going to do this way, right here, which I'll set aside for now, and then we're going to do this, we're going to do this the traditional way, and then we're going to do this way, right? So dy dx, how do we take the derivative of this implicitly in calculus 1? So first of all, you would do 2y times dy dx, right? And then plus, this is a chain rule situation, or no, a product rule situation, 2y plus 2x dy dx, and then minus 3x squared equals 0. Now I'm gonna group these together, dx plus what is it called? 2y minus 3x squared equals 0. Now, I'm going to solve it, but then I will enlighten you guys with the knowledge. So first of all, I'm going to solve it. So the solving is dy dx is equal to 3x squared minus 2y over 2y plus 2x. Right? That's very nice. But here's the knowledge enlightening. Here's the knowledge enlightening moment. If you multiply by 2x, this is what you're going to get. You're going to get this. This looks like something. What does this look like? This looks like the total differential. Does it? Doesn't it? Right? df. And usually df is really small. Your change in f is really small, so it's practically 0. The limit as f approaches 0, it's practically 0. df is 0. This is, if you take the f sub y for this one, 2y plus 2x. If you take f sub x for this one, 2y minus 3x squared. So you just come back to f sub y dy plus f sub x dx equals 0. So that's actually what we call the implicit function theorem. We're going to do it the other way though. This way is this is a really enlightening way. I think this is actually way harder to teach than the way that I'm about to teach you. This is pretty interesting, really interesting. So you can divide by dx, subtract f sub x, and then divide by f sub y. But this is the proper way that we're going to do it from now on. Set f is equal to the, oh gosh, wait, I erased the original function. So erase that. Set f equal to the left hand side. So f sub xy is equal to this. Now write out the total differential df, which we just wrote. We just wrote what the total differential df is. Df is equal to 2y, or no, df is equal to something dy, f sub y dy, and then f sub x dx. F sub x dx is, what's f sub y first? 2y plus 2x. And then what is f sub x? Is 2y minus, or no. Yeah, it is 2y minus 3x squared. Now divide both sides by dx. Very, it's quite you call like I call it quite like abusive notation. Divide both sides by dx, right? So df dx. So notice that f is always a constant. F is always a constant. It always stays 16. So df is 0. Right, it never changes. df is supposed to be changed in f, never changes, so it's 0. So 0 is equal to 2y plus 2x times dy dx, and then plus 2y minus 3x squared right here. Dx over dx is 1, right? Because the same thing divided by itself is 1. So it's 2y minus 3x squared. Now solve. Dy dx equal 3x squared minus 2y. And it's totally fine if you don't feel very comfortable using this method yet. You will feel more comfortable later on. But this is probably a simpler method than doing the product rule and being stressed about the fact that you might get the product rule wrong. In fact, you'll have to do it because we will have a function usually of 3 variables, and we have if we have a function z defined implicitly in a function of f of x, y, z equal to a constant like this. Let's say, I don't know, x squared. I'm just going to do a very simple one. X squared plus y squared plus z squared equals 4. Right? We could say f, big capital F, or I mean g, is equal to this, and then we'd say that f is equal to x squared plus y squared plus z squared. So df, right, df is equal to, I'm just going to put it down here, 2x dx, 2y dy, 2z dz. Now these are d's, but once you divide and like manipulate stuff, what you're going to end up getting is you're going to end up getting a partial instead of the d symbol. The only reason why we have the d symbol right now is because there is an actual change, right? It's not with respect to anything, it's just a change. But soon we'll actually have to use partials because it's a change with respect to something, and it's not the total change, but it's a partial change. So f sub x dx plus f sub y dy, f sub z dz. Y is independent of x, so dy dx is 0. We're not moving in the y, like if we are calculating like x sub z, this or no, this one is x sub c, or is it? I think it's supposed to be z sub x, but whatever. Let's say we're doing x sub z, and then yeah, so since x, y, and z depend on each other, we can actually calculate x sub z, x sub y sub x, y sub z, z sub x, and z sub y, all of those combinations. But let's not worry about that too much. So pretend to say is z sub x, this says z sub x, this says divide by d x instead of divide by dz. I messed up majorly, but so anyways, y is independent of x. We don't change y, right? So since we're not changing y, we're kind of keeping it constant because we're trying to calculate x sub z or z sub x. We're keeping y constant. We don't care about y. dy dx is 0, so we're not moving the y direction. Now we have f sub x dx plus f sub z dz. If we divide by dz, we get partial z, partial x, partial z, f sub x, partial z is plus f sub z is equal to 0. So in this case, this will be 2x and then 2z, and then you will get, this is negative z over x. So that's your partial, that's your x sub z for the function. This is a sphere, so it makes a little bit of sense, right? So that's the implicit function theorem. More complex chain rule. So sometimes maybe you'll be able to find some numbers, but you won't be able to find specific functions for them. And you only have functions defined in terms of other functions rather than the like other functions with other inputs that, or other outputs that aren't the thing that you want to find, but you know the equation for it, right? Like let's say the temperature depends on pressure, and the pressure depends on the number of moles, but you want to find a change in temperature in relation to the number of moles. You don't want to find a change in temperature in relation to pressure, and then the pressure in relation to the number of moles. You want to go that that kind of path straight up. That's that path, right? You want to go straight from temperature to moles. You don't want to go temperature to pressure, pressure to moles. That's kind of like the chain rule that we have initially, but this is a more complex chain rule because, well, you'll see. So notice, if g is g of x, y, and x is x of st, y is y of st, those are your two kind of other variables that you'll see. So this is dx. Notice you have dx and dx right here. You have dy and dy right here. So what does this mean? This means you can substitute, right? This is simply just, okay, x is x of st, so dx is just x sub s ds plus x sub t dt, right, if you're confused. So what does this mean? This means you can substitute. Dg is equal to g sub x times x sub s ds plus x sub t dt plus g sub y times y sub s ds. and it kind of all falls into like a smooth tree, right? I'm gonna use tree because we're gonna do something with trees. So this is what we'll get, right? This the differentials that we'll get right here. We know that what else we can do? We can distribute, and then we can actually group as well. So you'll get g sub x sub s ds plus g sub y sub s ds plus g sub x sub t dt plus g sub y sub t dt. Right? You can group these. So if we factor it into ds and dt, what we'll end up getting is dg is equal to g sub x sub s plus g sub y sub s ds plus g sub x sub t plus g sub y sub t, and in parentheses, of course, dt. Now g is a function of x, y, but g could also have been a function of st if we knew what s and t was. And I'll illustrate that with this example right here. If we knew what s and t was, we would be able to do it, but we don't in this case. So what we can actually do is g is as a function of st is simply just g sub s ds plus g sub t dt. Right, dg is equal to this, because we worked it out from this, but also this, because that's the chain rule, right? That's just the chain rule. So what we end up getting is this equivalency. This is equal to this, and this is equal to this. There we go. So tree strategy. What? Okay, wait. I have tree strategy down here. Don't think you guys know what that means. But this is what it means. So let's say we have a function g, right? Function g, and g is a function of x and y. X and y are both functions of s and t. So this is what we can draw. We can draw a tree, right? So what do we end up getting? G sub x, or dg, is g sub x sub s, g sub s, g sub x sub s plus g sub y sub s ds. Find all the ways to go to s, and then plus g sub x sub t plus g sub y sub t dt. There you go. So you want to find g sub s, just find all of the ways to go to s, this case, and if you want to find t, find all the ways to go to t, that case, g sub t. Or if you want to do it in order, you can just say dg is equal to g sub x sub s, right? G sub x or g sub x sub s ds, right? G sub x sub s ds plus g sub y sub s ds, or actually g sub x sub s ds g sub x sub t dt, g sub y sub s ds, g sub y sub t dt, right? If you want to write out the total differential in order, you can do that. Find a total differential in terms of s and t for f of x, y, and z, where x, y, and z are functions of s and t. So we do the same. F, 3 variables, y, z, s, t, s, s, t, s, t. That's a tree diagram. df is equal to f sub x sub s ds plus f sub x sub t dt plus f sub y sub s ds plus f sub y sub t dt plus f sub z sub s ds plus f sub z sub t dt. Easy as that. Really, really easy. And if you want to find the f sub s, right? F sub s, like this, g sub s. You just find all of the paths that it takes to go to s. F sub x, x sub s, f sub y, y sub s, f sub z, z sub s. That's the tree strategy. Find f sub s and f sub t, or del f partial s, and partial f partial t. If f of x, y, z is y, and natural log of x, natural log of z, x of s and t is this, y of s and t is this, and z of s. So you can do this two ways. The first way you can do it is you can just say f of s and t is equal to y, substitute it, 2t, natural log of x, s, natural log of e to the t, right? Or natural log of z, which is e to the t. That's equal to 2t times t times natural log of s, and that's equal to 2t squared natural log of s. So then f sub s, or partial f partial s, is equal to 2t squared over s, and then partial f partial t is 4t ln s. And that is really, really easy, right? And it's unfortunate that I came up with too easy of a function just to plug in, but sometimes, I wouldn't even say most of the time, sometimes functions are not this easy to plug in and just calculate like this. So yes, you can do this. You can just plug in x, plug in y, plug in z to the function, and then you will end up with this, which is really, this is really easy. Like, I'm actually pretty, I wouldn't say I'm proud of myself for making this easy. I was trying to make one that was hard. But anyways, let's do it. So let's draw the tree diagram. We already have a tree diagram from last time, so I'm not going to draw it again. Let's draw a tree diagram, or let's have a tree diagram right here, and then we will start. We can also copy this over. That's very nice. Like this, right? So what does this mean? So df is equal to f sub x. What's f sub x? F sub x is y over x ln z. What's x sub s is 1 ds, plus f sub x, again, y over x ln z, y over x ln z. And then what is x sub t is 0, right? So this is 0 dt. So this is gone. This is gone. Plus f sub y. What's f sub y? Is ln x ln z. Right, so in fact, since we know that, wait, no. Yeah, no, never mind. I'm ignoring me. Natural log of x, natural log of z, ds, or that's f sub y, I'm sorry, y sub s. What's y sub s is 0. So that's gone. Plus, now I know it's 2, it's going to be 2. Natural log of x, natural log of z, and then it's 2, because 2t, y sub t is 2t, right? This is dt. Plus, now we have e to the t, so ds is going to be gone this time, so which still calculate f sub z is y over z ln x times 0 ds, and then plus y over z ln x times e to the t. Now, what can you do? You can plug in the numbers. That's what you can do. In fact, I would probably recommend it. Or actually, you probably should group it. So this is dt first, dt. So let's group. let's group the stuff. So df is equal to y over x ln z ds. So that's your delta, that's your del f del s right there. That's your f sub s plus ln x ln z times 2. So 2 times ln x ln z plus y over z ln x and times e to the t dt, like this. Now we substitute. Now, this is actually, like I've said again, this is harder to do. With this, it's easier to do with just substitution. So y is what? Y is 2t, x is s, and z is e to the t. So it's just 2t over s times e to the t, or times natural log of e to the t, which is 2t squared over s. This is natural del f del t is equal to 2 times natural log of e to the t is t, so 2 times t times natural log of s, plus y over z is, what's y over z? Y over z is 2t over e to the t times the natural log of x. What's natural log of x is ln s again, and then times the e to the t. So e to the t and e to the t can cancel. 2t ln s and 2t ln s evaluates to 4t ln s. And that is your answer for del f del t. So yeah, both methods work, but this method is a lot more convoluted sometimes. Sometimes you'll be forced to use it no matter how convoluted it is. Anyways, okay, so I'm sorry about that. Something happened for me to be not able to do this final problem, but it's the next day now, and we're going to do the final problem. Find z sub r and z sub r are given. Z equals g of xy, x equal r minus s, y equal r squared plus s squared. So we can always draw our tree diagram, right? So z is a function of x, y, and x is a function of rs, y is a function of rs. So this is how you're going to find z sub r. Now z sub r is going to be scary. It's going to be really, really scary, but we're going to be able to find it out soon. And we're going to be able to find out how to solve that. And if you want to think about it, you can stop this right now, solve c sub r by yourself, or stop it when I solve z sub r, try to find z sub r by yourself. You can try to find it. It's a little bit kind of niche, kind of good to think about. Anyways, so this is how you get it. So z sub r is equal to what? Is equal to z sub x, x sub r, z sub x times x sub r. What's x sub r? X sub r is 1, right? And then plus z sub y, y sub r. What's z sub y? Z sub y is z sub y, and then 2r, right? This is, we don't know what z is. We don't know at all what z sub x or z sub y is. It's just a function. I'm just say function g of x, y. So it could be g sub x plus g sub y for what I know. Okay. So this is your function right here. This is 2, not z, and I need to draw my 2's better. So right here. So now what do we get? We want to find z sub rr, and I'm just gonna write it like this, just so that it's a little bit easier. Right? So it's partial derivative. This is like an operator. So partial derivative with respect to r, like this, z sub y times 2r. So what does this mean? What does this mean? This means we're taking, okay, give me some space right here. Partial r partial z partial x. That's what it means. And notice that z, or partial z partial x, is z sub x. But z sub x is also a function. It's also a rule, right? G doesn't, or z doesn't only have to be the thing that's the rule. Z is equal to g of xy. But z sub x is the partial derivative with respect to x, but it's also a rule. It's not a number or anything. It's a rule. So it's its own function. And its own function can also be in terms of f of x and y. So what you actually get is z sub x, and that can be in terms of x and y, and that can be in terms of r, s, like that as well. Right, and x, these are definitely in terms of r and s, but z sub x is also in terms of x and y, because just when you take the derivative, for example, if z is like x cubed plus y cubed, right, z sub x, or no, I'm sorry, this is a bad example, y squared x, z sub x is 3x squared plus y squared, right? It's still in terms of x and y. It's not a number. It's not a complicated thing. It's not like an abstract thing like dx. It's still a function. So because it's still a function, we can still do it the way that we have always done it, and that is find the derivative, find the partial derivative with respect to r of dz dx. How are we going to find that? We're going to find that by doing this. So what do you end up getting for d dr dz dx like this? This is equal to z sub x sub x, z sub x times x sub r plus, right, so you're taking z sub x, taking a derivative with respect to y, z sub x sub y times y sub r. And that is your first function right there. Now next is dr of dz d, or partial z partial y, is z sub y sub x times x, z sub y sub x times x sub r plus z sub y times y sub r, right? That's what you get when you take the derivative. And I'm going to make this, I'm going to put it kind of, make it a different color and then put it in the corner, because this is important later, because we need a substitute now. So you get z sub rr is equal to the derivative z sub xx, z sub xx, x sub r, plus z sub xy, y sub r, plus, and we need to move this a little bit because this is a product rule situation. Z sub y can be, is functions of x and y, each could be function of r. So z sub y can be a function of r and s, right? 2r is definitely a function of r and s. Take a derivative with respect to r, what you end up getting is, what do you get? So you get this, the derivative of the first, z sub y sub x, x sub r, plus z sub y, y sub r. In fact, I'm just going to put x sub r and y sub r in. So x sub r is just 1. So I'm just going to erase these. And then y sub r is 2r, right? Y sub r is the derivative, partial derivative of y with respect to r. So it's 2r right there. And all of this is multiplied by not the derivative of the second, just the second, 2r, plus z sub y like normal, not the derivative of the first, derivative of the second. What's the partial derivative of r with respect to 2, or what's the partial derivative of 2r with respect to r? It's just 2. So it's 2zy. So what you end up getting is zrr, z sub rr, is equal to z sub xx plus, and what I'm actually going to do is combine these two because this is continuous. We're going to assume it's continuous. Z equals g of xy is continuous. So 2r plus 2r is 4r z sub xy plus 4r squared z sub yy plus 2z sub y. And that is your answer right there. And if we plug numbers in, it should work. Right? You can try to plug numbers in. I will, I don't know, or if you can try to make a function for g equals x squared plus xy minus y squared, something like that. It should work, right? It should work. Will it work? I don't know. I'll probably try it after this video. But that's it for today, or that's it for 3.5. We will do the directional derivatives and gradient vector next. I'll see you guys later.